So, afternoon again, everyone. We are going to be continuing with module 3. So, in last class, if you all remember, which was just the other day, right? The last day we did the evolution of the atomic model really quickly. And we did Millikan's oil drop experiment. And what were the implications of Millikan's oil drop experiment? That the electric charge on an object is multiples of a certain value, and that is how they were able to work out the charge of an electron to be 1.6 by 10 to the minus 19. So it was just a back working kind of thing. So it's a very easy calculation to do where we use Q, which is your charge of your electron or your charge of your oil drop, right? Q is equal to your by mass, by gravity, by the distance that your drop had traveled and then became stationary between your ground plate and your 500-volt plate. And V would be your voltage. So just to calculate, and you would end up getting the charge on your oil drop. And it's easy to go and work out the mass of your oil drop using density and volume. So that is just a very brief um, run through of what we did the last day. So we're going to go on today, brand new topic. You've never done anything like it, never. All right, so we're going to look at the particulate nature of electromagnetic radiation. Now, this is a whole bunch of contradictions because when we start investigating how matter and materials and space and everything behaves, the more we look at it, the more unique it seems, the more unexplained it is. We actually have a branch of physics where when you observe the experiment, it behaves differently when you do not observe it. That's called quantum effect. The quantum effect is when we look at something, look at an experiment, we may get results A and B, but when nothing is looking at it, as in it's not being observed, not being recorded, you might get results C and D. It's extraordinarily weird. All right, they have explained why that happens, but that's not our purpose today. So just to look at how we're going to end up entering the world of contradictions or the worlds of opposites existing together. Particulate nature. Particulate means particles, means matter, means things that have a mass and behaves like mass. Particular nature of electromagnetic radiation. Electromagnetic radiation, which is anything along the electromagnetic spectrum, which is from radio waves all the way down to gamma rays. And we know gamma rays and all of these rays don't have a mass, don't have a charge. So, how on earth can radiation have a particulate nature? All right, so again, this is how physics came up. Once they broke open the atom, it was a snowball effect. They started understanding more of the atom and how matter itself behaved at the microscopic level. Microscopic not being electron, not being atoms, actually, not being cells, it's atoms and subatomic particles. So photoelectric effect. This used to be in the CSEC syllabus when I was in school, so they've put it up into the CAPE syllabus now. So let's just read. This is the emission of electrons from the surface of a metal with the help of electromagnetic radiation. Using the study of the photoelectric effect, several aspects of the nature of atoms were found. So what is the photoelectric effect? It's a very simple idea of if you take a pen, right? If you take a light, any sort of light source, we usually use UV light or something, and we shine that light onto a particular type of metal, right? If we shine it onto a particular type of metal, if that light has the right frequency, that frequency of light gets absorbed by the metal and it gives the electrons enough energy to leave the metal. So if you want to take really bad explanation, which has nothing to do with it, by using a particular type of electromagnetic radiation, we can cause metals to evaporate. That's using it to the very simplest terms. You would think like, what? we can go and shine a light, not visible light, but we could shine a light on a metal, and that metal can now start to evaporate. We're not saying it would disappear. Remember, evaporation is the process of losing your surface atoms. That is the process of evaporation. Here, if we apply a light, chat. No, Jabari, you did not find your way. There are limitations, a lot of limitations to this. All right. So what they realize, and this is actually this topic of the photoelectric effect is the field that Einstein got his Nobel Prize for. He did not get his Nobel Prize for relativity. He did not get his Nobel Prize for gravity waves. He got it for work in the photoelectric effect. Watch how everybody get fooled. All right. I didn't know this too until like about 10 years ago when I actually looked it up. So the photoelectric effect, and here how curious this is. If you take a electromagnetic wave, an electromagnetic wave of a certain frequency, and we know frequency, as your frequency change, we're going to go into different categories of waves. So that's how we go from radio to micro to infrared to visible to UV to X-ray to gamma, right? And if we use a light of a certain frequency we say, certain metals absorb that energy, right? And that energy is able to cause surface electrons to be liberated and become free flowing electrons out into the air. We're not talking about free flowing electrons as an electric current. That's something else, right? Here you can actually cause the electrons to be liberated from the surface of the metal, which is an extraordinary result, right? If you want to put it, as I said, layman term, I shine a torchlight on a metal and it starts to evaporate. That's kind of, y'all, blow your minds kind of thing. So let's read here. Using the study of the photoelectric effect, several aspects of the nature of atoms were found. So when they got over their excitement as to the implications of this experiment and the results, they now started to think. Remember, they are now well outside the box. They've expanded beyond the box, and it started with Rutherford. He thought about, unexpected results means something is happening in the atom. It's no longer our equipment is wrong, our equations are wrong. It means that something is happening we don't know about as yet. So here, obviously, they've learned, let's look into the atom. The atom is where our answers lie. So what they realized here, one, the number of photoelectrons or the electrons emitted by the light emitted by the metal are called photoelectrons, which makes sense. Photo means light, electrons are electrons. So photoelectrons are electrons that have been liberated from its metal by using light. Not visible light, but light being any sort of radiation or radiation from the electromagnetic spectrum. So the number of photoelectrons emitted per second is proportional to the intensity of the incident radiation. What makes, all right, yeah, so the number of photoelectrons emitted per second is proportional to the intensity of the incident radiations. Two, the photoelectrons are emitted with a wide range of kinetic energies from 0 to maximum, which increases as the frequency of the radiation increases and not the intensity. Pay attention, we have two very important terms here. We have frequency and we have intensity. Two very important terms in this topic. For a given metal, there is a certain minimum frequency of radiation called the threshold frequency, below which no emission occurs irrespective of intensity. So an example, the photoelectric effect for zinc lies in the ultraviolet range. Ultraviolet being the step up from visible light. So let's just see what this all means. Let's start from 3, go up to 1. Once I have my metal, if I have my metal, all right, this is my metal. Let's put a little circular metal, and I'm shining a light on it. That light, or that radiation that we're shining on it, that electromagnetic radiation that we are shining on it is going to cause photoelectrons to be emitted and liberated from the surface. Only when we have the right frequency, it has to have the very, very correct frequency, is the metal able to absorb that light. If we do not have the right frequency, those electrons or those photoelectrons unique to that metal will not gain enough energy to be liberated. Now, how do we know energy is related to frequency? You know, energy is equal to half mv squared. We know that, all right? And in this case, we know energy is also equal to, we know that velocity is equal to frequency by wavelength. Here, intensity has nothing to do with how fast our wave is moving. It has, or how much energy our wave has. So if you look here, frequency, velocity is actually going to be equal to half mass by frequency by wavelength squared. Frequency is what enables or tells us how energetic our wave is, right? And let's see the basic rationale as to why frequency tells us how energetic our wave is. What is frequency again? Anybody? Simple physics here? Anyone? What is frequency in simple terms, physics terms?
I feel like I'm overthinking.
Yeah, real simple. I'm talking about how do we know what frequency is? In very, very simple terms, my wonderful, wonderful children.
Frequency is 1/10.
Yeah, in simpler terms, what is frequency?
How long it takes one oscillation? No, that periodic time.
My beautiful children who are writing exams in 2 months. What is frequency?
See, waves on the syllabus now, right? So that was last year.
Frequency. You see, this is where I wish I was here in class. I felt every single one out there. Right? Frequency basically tells us how many waves are passing in a given second. Right? If I have a frequency of 1, that means 1 wave passes in 1 second. If I have a frequency of 0.5, that means, no, a frequency of 2, that means I have a wave passing, 2 waves passing in a second. If I have a frequency of 1,000,000, that means 1,000,000 waves pass in 1 second. So which one do you think is more energetic? The frequency where 1 wave passes in a second, or when we have a frequency of 1,000,000 where 1,000,000 waves pass in a second? Which one is more energetic?
A million waves.
A million waves, right? This is why frequency is a measure, right? Not amplitude. Amplitude doesn't tell us how much energy the wave has. Amplitude just tells us how much power has been added to the wave, right? Frequency tells us when a wave is more energetic because we can tell how much is moving in a given point of time, right? That's the simplest way. So here, in order for our metal to liberate a photoelectron, it must have the right amount of energy delivered to it. And what delivers energy to a wave? It's frequency, right? Not the wavelength. The wavelength is just the size of the wave, right? But here, frequency tells us how much energy, the energy of a wave is contained in its frequency, which you're going to see just now coming up in equations. So first things first, you must have the right frequency for your photoelectric effect to occur, and this is called your threshold frequency, right? So you can reach a frequency, say it's 9 million hertz, not yet 10 million hertz, 11 million, yes, you reach the right frequency for a given wave. Right? So you need a certain amount of frequency, meaning the wave must have the right amount of energy to liberate a photoelectron from that material. So let's say this wave now has the right frequency. It has the correct frequency that's going to allow those surface atoms to absorb the energy and emit a photoelectron. So here, let's read the second one. The photoelectrons emitted range in kinetic energy is from 0 to maximum and increases as the frequency of the radiation increases. That makes sense. I'm not going on to this yet. Wait, I'm coming to that. Right? Frequency is what gives the energy to your waves. So if, imagine here, let's just use this example. Suppose my threshold frequency is 5 by 10 to the 7 hertz, right? And above that, so that's my threshold frequency, right? My threshold frequency is 5 by 10 to the 7 hertz. I shine a light of 5 by 10 to the 7 hertz on that metal. This is the minimum amount of energy needed to liberate that photoelectron. So that means the electrons coming out of here going to have a little bit of energy towards them because it's just enough to cause them to get liberated. Now, suppose I shine a light of 1 by 10 to the 8 hertz. This is twice the amount as the one before. So now clearly we have a wave that has enough energy to knock out those photoelectrons. And this is where Newton's second law applies, but not really. But if you were to look at connecting classical physics to now, we know applying Newton's second law, when you hit something with a certain amount of force, it's going to move just as far or further because of the amount of force applied. Remember, the rate of change of momentum is directly proportional to the applied force and takes place in the direction of such force. Kind of the same thing. If you use a little bit of energy, right? If you use a little bit of energy, just enough energy to move out that photoelectron is just going to move, right? I mean, if you just touch a little ball or something with enough energy to move it, it's just going to roll a little bit. But now you add a lot of energy and you hit it really hard, it's going to fly out and it's going to move very fast. Similar thing happens here, right? So here, once we have the frequency of the radiation is enough, our emitted photoelectrons will have greater and greater velocities when our energy is large enough. Please note, let's say here, let's read about number 2 without all these lights on it. Number 2, the photoelectrons are emitted with a range of kinetic energies from 0 to maximum, which increases as the frequency of the radiation increases and not intensity. What gives the energy? The frequencies. So I could go and take, let's think about it. I can take a little laser light, those little cheap laser lights. Tiny laser light that we use in the experiment in lower 6. Pen, why are you doing that? All right, little tiny laser light, and it shoots a light towards the metal. If it has enough, the right frequency, it is going to cause photoelectrons to be emitted. So it doesn't matter how bright this was once we have the correct frequency. Now, suppose I go and take one of them big bulbs I want to bust up every day. I watch these every day and want to bust them up. Right, the big floodlights in the stadium lights. Say I get one of those big, huge floodlights. And if you look at it, you know you're going to go blind for the next couple hours. And shine that light onto this metal. The light from those floodlights is usually about 6 by 10 to the 7 hertz, right? And the one we're going to use in a laser light, suppose we use ultraviolet light, suppose we're going to have 8 by 10 to the 9 hertz. No matter how strong this light bulb is, right? We can take a big, huge light bulb and shine it onto that metal. If it does not have the right frequency, right? If it does not have the right frequency to cause those electrons to be liberated, it will not make any of those electrons leave the metal. The metal will faster melt from the heat before those electrons are liberated. Kind of, right? Blowing your mind kind of thing, right? A simple little light, it could be a small little light. Once it has the right frequency, photoelectrons are given off. If you don't have the right amount of light, you can take the biggest, huge light bulb, shine it on it, melt down the metal, and photoelectrons have still not yet been emitted because that energy, that frequency of energy needed to liberate those electrons are not there. It's not enough. All right. And then coming up to the last point, see how these points were kind of backward. I don't know why the book had it like that. Last point, point 1, the number of photoelectrons emitted per second is proportional to the intensity of the incident radiation. So now let's go, we have the right light, right? Being the right electromagnetic wave being shone onto your metal. So now I have the right light here where I have the correct frequency. Every single ray of light that hits that metal is going to get absorbed by the metal and cause photoelectrons to be emitted. Now, if I use, this is the correct light. Remember, guys and gals, light meaning electromagnetic wave. Now, suppose I use a bigger light of the exact correct frequency, of the needed frequency for this experiment or this situation. Suppose I now shine on more of this, which is intensity, is just more of your waves available. Guess what's going to happen? We're going to have more and more electrons being liberated because why? We have more of the waves that are able to liberate our photoelectrons present, thus making it possible to create more photoelectrons. I hope that was sufficient explanation for it. So let's just go through that again. What is photoelectric effect? It's where we shine a electromagnetic wave onto a metal of the correct frequency to enable photoelectrons to be liberated. Photoelectric effect depends strictly on the frequency of the radiation and not the intensity. But once we have the correct frequency, the intensity is going to increase the amount of electrons liberated. All right, so let's go on. There are a few problems associated with the photoelectric effect. As cool and awesome as it was, now that everyone is thinking out of the box, they've started to think too much, which is good. Thinking too much is a good thing when we face the new world of physics. This is a new world of physics by the way, guys. All right, so using point 1, which is once we have the correct frequency, intensity is going to increase the number of photoelectrons emitted. Using point 1, one would assume that the kinetic energy of the photoelectrons would increase as the intensity increase. This does not happen. Classical physics does not explain. Honestly, let's think about it. If I use a bright light, I use a brighter and brighter light, that should tell us, a little common sense, right? No, yeah, common sense, right? If I shine a really bright light onto this metal, I should get more and more powerful rays. I don't, more powerful photoelectrons. I don't. What I do get, I get more photoelectrons. What increases the velocity of these photoelectrons? Using a higher frequency. What gives us energy, and energy is usually expressed by velocity, is your frequency. Intensity here is just going to give us more. More and faster is not the same thing. All right, so classical physics had no explanation for this. They had no explanation. So why, if we don't use more of something, shouldn't we get more energy being transmitted? That makes sense. If I want to heat up a room, I'm not going to use a fire of a different type. I'm just going to use more fire. All right, you all see the little contradiction here. right? If I wanted to heat up a room, I'd use a bigger fire, I'd use a greater intensity of fire. But that's not what's happening. They could use, as we said, as big, a huge, massive amount of light. And if it does not have the right frequency, photoelectrons gonna sit on here and go, what's your problem? Why are you harassing me for? Why are you melting me right now? Honestly. Right? So classical physics had no explanation for this. So this is where a newer branch of physics that looks at the interaction of matter and electromagnetic radiation was developed. What is that new branch of physics? Quantum physics. This was the birth of quantum physics. One experiment, Geiger Marsden, blew open the atom for us. As in, we discovered the pathway into the atom to discover the atom. Right? This one experiment, the photoelectric effect, blew open and exposed us to the world of quantum physics. We still don't understand it properly. Eh? Don't worry, I don't understand it properly either. Similarly, and this is the worst one, right? This one here is what would blow your mind when you think about it, as in the realm of classical physics. Classical physics is the physics we do from everything Newtonian physics, right? Newton laws, everything you've learned in school is classical physics so far. Similarly, one would expect that radiation is applied, that when radiation is applied to the surface of a metal, that a little time would pass before the electrons are emitted. Well, yeah, that makes sense, right? If I have to make electrons gain enough energy to leave the metal, so suppose I have a surface here and I have, why would you do that? All right, let's see. Surface of my metal, and I have electrons in them. I have electrons in the surface of this metal, and I'm shining a light onto this metal. It would make sense since these electrons are bound by chemical bonds, electrical chemical bonds to the metal, that you would need for the atom to gain some energy. These electrons have to gain some energy. They have to start to vibrate faster to the point where it breaks its bonds and now becomes a liberated photoelectron. That doesn't make sense, y'all? Y'all can give me a thumbs up if y'all feeling lazy to answer. Or yes. Wouldn't the concept of if metal having to have the light shone on it for a little bit of time, meaning it has to warm up before it emits photoelectrons, make sense? That is what makes sense to us, right? As in, a little time has to pass. That metal has to, again, in inverted commas, warm up before we can emit photoelectrons. Same thing like our light bulbs. You all realize when we put on, especially these LEDs, they start off kind of dim, and then it takes a little while to turn on. Yeah, a certain amount of energy is needed, right? Same thing, it's faster for incandescent bulbs. If you use it under a very high speed video, right? You're gonna see that it takes a while for that gas to heat up, and then it glows and forms, gives us our light bulbs. It doesn't turn on automatically. It takes a little bit of time, but it still takes time. A little bit of time still means time. So this is what we expected to happen, being the physics world. So the one would expect that time had to pass before the electrons are emitted, since enough energy should be gained by an electron before it can escape. This is where they realize, wait a minute, this is not happening. This does not happen. The photoelectric effect is instantaneous, meaning absolutely no time passes from the time that light hits the metal to when the electron is emitted. As in, as soon as the light hits the metal, an electron springs out. Right? It's so fast, it's almost like the light is bouncing off of the metal. It's that fast. Right? In physics, classical physics has no explanation, has no room for instantaneous events. There is usually a sequence of events that occurs first. As I just said, it has to gain enough energy, it has to start to vibrate. bonds are broken and it becomes liberated. That is what we knew. This is not what was happening. It behaved as if as soon as the light hit the metal, it hit out a photoelectron. It was an instantaneous reaction or instantaneous event. Classical physics has no room for that. We must have an energy transfer. That's why we have the law of conservation of energy, right? The law of conservation of energy, as far as we knew, did not apply in classical terms to this. This explanation is found in quantum physics. This is why I said this experiment gave us our first look into quantum physics. Not to say quantum physics was invented. It's not to say gravity was invented or discovered, right? All we know, we are now able to understand that it's there, and we have started to now take our first footsteps into what the quantum world of physics is. And here we are looking at how matter behaves at the very, 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 very microscopic level, beyond microscopic level. We're looking at fundamental levels where we look at the matter that makes up an atom, and below that. If you want to go and try to read us up, but y'all, we're not going to try to read us up today. But if you want to read up why photoelectrons are emitted from a metal, you could do that. So the quantum theory. In the 1900s, Max Planck, it is with Max Planck is the one who discovered the photoelectric effect. He had gotten his Nobel Prize for discovering the photoelectric effect. And then he worked together with Einstein to go and do more work in the photoelectric effect. So Max Planck was investigating black body radiation. You all should remember black body radiation. At this time, it was proposed that energy flowed continuously, but Planck supposed that energy was emitted in intervals or quantums of energy. Quantums of energy is a brand new term for us to pick up. Quantum of energy, let's see what that is. Quantas are whole numbers, and an object can only emit whole numbers of energy. Meaning, we thought before this that if an object, let's say we have a candle giving off energy, giving off heat energy. As far as we know, don't we write down a straight arrow anytime we have to do this, or when we're looking at sun to indicate rays of sun coming out in a straight arrow, meaning things are constantly being let go from that, or energy is constantly being emitted from that source. That's what we know. That's what they made sense to them. But remember, just before this, they realized that charge existed in multiples of a fundamental amount. That fundamental amount was the charge of an electron, right? Electrons do not come in half charges, do not come in 1/3 charges or 1.5 charges, either 1, 2, 3. So coming from that realm of thought, he proposed similar, that energy did not flow consistently out of any sort of energy source. It is actually emitted in little packets of energy, little pulses of energy. Now, of course, if a pulse is very, very fast, it's going to look like it's continuous, right? But he proposed that energy was not a continuous flow, but pulses. And those pulses were called quantums of energy, hence where we get the word quantum physics from, right? So he proposed this is a whole brand new concept, completely different from the hundreds of years of physics foundation we have by then. And trust me, the foundation by then was very, very, very significant. So he proposed something very different, that energy flowed in little packets, right? Little pulses of energy. So according to Planck, the quantum energy of radiation, being any sort of electromagnetic radiation from radio to gamma that we know of so far, there could be things bigger than gamma. There could be things smaller than radio, right? He said that energy given off by electromagnetic waves is the equation of E is equal to HF. Right, this is where he looked at the relationship between energy of a wave and the frequency. He realized there was a relationship, and this came straight from the photoelectric effect, meaning we knew we needed a certain amount of energy to liberate our photoelectrons, and the only way we got that energy is by changing our frequency. So clearly there's a relationship between frequency and energy. So he did experiments, he did the calculations, he did experiments to try to investigate what is the relationship between energy and frequency. There must be some kind. And this is why I call the ultimate ratch of all time. The ratch that invented a whole, well, exposed us to the whole new world of quantum physics. And that is Planck's constant. We call it a ratch because there's no way at that time they had any equipment. Pen, behave yourself. Okay, all right. There is no reason at that point, at that time, or way they had to work out equipment that could work out things as sensitive as 6.63 by 10 to the minus 34. And you all saw how easy this was to work out in the lab. Secondary school equipment, and we worked out pretty damn close to this value. So he was doing experiments using frequencies of light, right? So they used different frequencies. They didn't have diodes back then, so they used like sodium lights, mercury lights, and lamps and stuff that gave off different frequencies. And by using different frequencies of light, he used the same voltage. He switched the voltage or increased the voltage to the point where those frequencies of light worked and was able to back calculate Planck's constant. Remember we did it? EV. What was the equation we had used? EV is equal to HF. All right, we're going to look what EV is just now. They had discovered this by this time already. All right, so it was very, very simple to work out the energy of your light and to work out Planck's constant. So Planck's constant was a derived constant initially. Please note, I didn't say it's a ratchet that remained. They used more sophisticated equations and experiments and data to prove Planck's constant. But with the equipment he had then, that's how he was able to get the Nobel Prize. You don't get a Nobel Prize from theoretical work, right? You have to be able to go in a lab and prove it. That's why Einstein didn't get relativity. Didn't prove it as yet. All right, so that's how they were able to prove, to find Planck's constant, where the energy is equal to E is equal to, H is equal to E upon F. All right, so here Planck's constant is very, very simple. All right, equation of E is equal to HF. This is our equation one. This is our first equation in the world of quantum physics. All right, this is our base equation. If we were to look at it at any other topic, this is essentially V is equal to IR. As common, as important as V is equal to IR is in electricity, in quantum physics, E is equal to HF is our base equation. Because of the small values used, it is convenient to express energies in terms of electron volts. So because we're looking at very, very small numbers, look at this. Using very small numbers is going to give us problems when it has to do with calculations and making mistakes. We're human. We make mistakes. We write down numbers wrong, as you all know. We put our decimal points in the wrong place. We put the wrong index in our standard form. All right, so what they did, they came up with a way to express these very small values, and we named them a new value called electron volts. Electron volts is a way of expressing energy. It's a new way or new unit for energy. So let's look at it. So they have here 1 electron volt is equal to 1.6 by 10 to the minus 19 joules. Anybody could remember if there's a relationship between energy, electrons here will be charge and voltage. Anybody? Is there a relationship between energy, charge, and voltage? My people who are doing exams in 2 months.
E is equal to QV.
E is equal to QV. E is equal to QV. And if I wanted to get the charge of one electron that has a voltage of 1 volts, all we had to do, right, is just multiply the charge of that one electron, 1.6 by 10 to the minus 19, multiplied by the charge if that one electron had a voltage of 1, which is our most fundamental number, 1, right? We're going to end up with 1 electron volt, which is the amount of energy that one electron has, is going to be the same thing as its charge, just in joules. So it's going to be 1.6 by 10 to the minus 19 joules. So if you ever get stuck in determining what 1 electron volt is, you all don't even have to remember what is 1 electron volt because it's the same numerical number as a charge. So if you want to write that down, you can go ahead and write it down, but it's in the video. You all can, yeah, write it down. So let's just wrap this up and we will stop here because I want fresh brains before we go on to the new equations, because that's going to take a little bit of derivation to do. All right, so continue reading. When Planck released his findings, Einstein did further derivations that properly describe the photoelectric effect. He assumes, or assumed, past tense, he's no longer alive, right? He assumed that not only will light and other forms of electromagnetic radiation emitted in quantas, but were called photons. So he gave the name photons. So what is a photon? A photon is not the weapon that they use in Star Trek. Anybody know about those? Are too old for that, or you're too young for that? Right. Anytime using anything from the electromagnetic spectrum. So if we have the entire field of the entire range of electromagnetic spectrum going up from radio, going straight down to gamma, anytime it emits a little packet of energy, and remember he proposed that energy was not a constant thing, it was released in packets. Now, of course, if packets are very, very high speed, it's going to look like it's continuous, right? And each packet of energy that is being released is called a quanta of energy. And this quanta of energy is called a photon, right? Photons are simply the packets of energy that are emitted by electromagnetic or are contained by electromagnetic radiation. So what they're doing, they're just recategorizing, renaming all our parts and whatnot, because we are in a brand new world of physics. Let's not confuse it with regular classical Newtonian physics, because Newtonian physics don't work here. Classical physics don't work here. All right, something else behave. This is where we said quantum physics being some experiments perform differently if somebody is observing it. Meaning if I'm looking at it, you are looking at it, if I have a camera set up looking at it, it will give us different results than if you just let it run on its own with no recording devices. You will get different results every single time. Quantum physics are very, very odd branch of physics. So here, photons are simply the packets of energy that are emitted or that electromagnetic radiation are transmitted by. So we will stop there because we have new terms to learn here. From here, we're going to start doing the full maths. But let's look into what we're going to be doing next day. When do I see you all next? I will see you all next week. Monday, Tuesday, Wednesday, next week, Thursday. Right? I only see you all once next week. You all want to have a next class sometime next week? Anybody? We only have one class on the timetable next week, because if Monday is day 1, I will only see you all on day 3. All right, so you all decide. You all talk among all yourselves and tell me a day. All right, because I want to go to school with my Form 4s soon.
Which day next week will be good for you?
I'll look at your timetable. If your teachers, anybody has to go back in school for anything, for any of your labs?
Not I.
Anybody else? Or it's only 5 of you all here. All right. If you look at it, it really doesn't matter who can come or not. It's a recorded class. I'll just post it up. All right. So we're still recording. So let's end that recording. We'll have a discussion. So we're going to finish this here. All right. So we're stopping right after photons, and we're going to go on to the photoelectric effect. We're going to look at the basic equations of quantum physics the next day.